Indeed, a pleasure to introduce to you this afternoon Dr. Benoit Mandelbrot, who presently is Sterling Professor of Mathematical Sciences at Yale University and Research Fellow Emeritus at the IBM Thomas J. Watson Research Center. Professor Mandelbrot is truly a man for many nations. He was born in Warsaw, Poland, and in the second decade moved to France, where he subsequently received his doctorate from the Faculty of Sciences at the University of Paris. And he has spent most of the latter half of his life in this country. Many people, however, associate him more closely with another country, Great Britain, because he asks in the title of one of his widely known papers, "How long is the coast of Britain?" Here he points out that the coastline is self-similar under a magnification, so that its measured length will depend upon the length of the measuring stick. The shorter the stick, the longer the coast. And indeed, if it were not for the incessant waves and tide, so that arbitrarily short stick could be used, the length would go to infinity. His continuing pursuit of the phenomenon of self-similarity, which he has recognized not just in coastlines, but in a wide variety of natural systems, ultimately led him to coin a word that is now familiar to nearly everyone, fractals. And today his lecture title will be Fractals in Science, Engineering, and Finance, Roughness and Beauty. His list of honorary degrees and medals and other honors is far too long for me to have memorized. I could read it to you, but this would cut deeply into the speaking time that is rightfully his. So if you need further evidence of the stature that he has attained, simply look around at the crowd that had filled every seat 10 minutes ago. Without further ado, then, let me introduce Professor Mandelbrot.
It is indeed a delight to be here among you, and in particular a delight to be introduced by Ed Lorenz. We met actually around 64 when a mutual friend, Erik Molo Christensen, told me, well, there is another man in a doghouse, not quite yours, but a bit further. And so you two lost souls may find some interest in common. Well, Erik was very, very, very clear-sighted, because indeed the work of Professor Lorenz and mine have very many points in common, even though they never quite identically the same field. Now, the title you see on the screen here is one which in a certain sense summarizes my whole life. I've been writing papers for about 50 years, which is a fairly long period of time. And as time went on, many people asked themselves what was the leading thought which permeated all my changes of interest from one field to another. And frankly, my answers were rather cumbersome. It's only lately that I realized that everything was very simple. All my life, I've been working towards what may perhaps become a theory of roughness. Now, let me describe this phenomenon of roughness. If we think of which shapes in our ordinary evidence are smooth, well, there are very few. Plain, perhaps for a child of primitive man, a child of once upon a time, quite a piece of water without wind. Circles, well, full moon, the pupil and the iris of the eye, a few more shapes like that. Straight lines, very few. On the other side, the rough shapes are absolutely without number. Wherever we look, we see shapes which are very, very complicated. Now, the history of science, as I see it today, after experience in many sciences, very definitely continues to be dominated by its origin. And science began with our senses, the eye, the ear, the feeling of hot, the feeling of heavy, the feeling of rough, the feeling of sweet or sour or acid. And each of these senses, except one, gave rise in due time, early on actually, to a science. More precisely, each went through three stages. For example, in acoustics, the idea of sound was known from time immemorial, since music always existed, and scales were known also. But the association of sound with frequency is the beginning of acoustics and developed in a very strong fashion. It developed mostly by a procedure which I'm going to describe, which is very important, I think. Acoustics did not try to represent all sounds. That's impossible. It focused on the sound of idealized strings or pipes and did a marvelous job with them. For drums, for concert halls, acoustics is not so terribly perfect. But that is not a criticism. A science does not have to be perfect. A science must find in one aspect of the mess of our senses some substantial part for which a theory can be done, and this theory must also give insights about the cases to which it does not strictly apply. And at this point in time, much of the effort of many scientists is naturally enough devoted to developing those senses which I described, and also, of course, to link them. For example, unified field theories propose to link the feelings of heavy and the feeling of light and weight. But in all this extraordinary effort, one sense has become totally deprived of implementation in science, and that's a sense of roughness. The problem goes very, very far back. Being very much one of those nuts who read old books, I was very impressed to find in Plato, one of his dialogues, a list of senses, and what I just said, the science is corresponding to it. And then he says, roughness is, well, he didn't say much about it. And roughness indeed turns out to be far more complicated than the other sciences, to require mathematics which has a markedly higher level of complication and of difficulty. So what my whole life has aimed at was to find regularities, invariances, since science is only a study of invariances in our experience of roughness, which might apply throughout and might provide tools for attacking roughness in all its aspects. So when I say that fractals, which is the word I coined for a certain kind of orderly roughness, they occur in mathematics. I will give you at least one example. The sciences, I'll give you a few examples in passing. Engineering, in finance, I'll spend some time on finance. Now, sometimes one wonders why all these various topics are brought together. They're not brought together for any fundamental reason, except that they all exemplify, once again, this very simple and fundamental issue, the question of roughness. So, as I see on first line, fractals are simple, complex, and open-ended. What do I mean by that? If one begins to define fractals without the kind of cloud of sophistication, rigor, and mathematical elusiveness, which was given to them for quite a while when they were purely part of mathematics, if one forgets about these complications, they're extremely simple. In fact, children are taught these ideas very, very early on. But these very simple rules create extraordinarily complex reality. And very rapidly, as I will show you shortly. And it's open-ended in a sense that one very rapidly goes to problems of such extraordinary difficulty that the best minds are struggling to cover them. Now, everybody knows me for pictures, and for some pictures which are quite glamorous. I'm very, very happy about them. I'm delighted that an instrument like the computer, which at that time was devoted entirely to arithmetic operations and the like, could have been tamed for the purpose so different from its original purpose. But my experience is that if I start showing you pictures, I will never end. Great fun for you, for me, but it's out of place. So I will simply not dwell on them. I will just show you this one. Well, let's now get to my point. What is roughness and how to handle it? Well, it's very appropriate that this auditorium is in a building of earth sciences, because an earth scientist, Mr. Wheatcroft, gave me this picture. He told me that when he teaches geology to his students, he's very careful to tell them at every given time, always put an element of scale. Because if you don't put an element of scale, you'll forget how big the thing was after which you photographed. So you put yourself, a camera cap or something in it, and then you remember how big it is. Otherwise, you forget. You confuse a pile of rocks and a mountain. Well, here is an example, indeed, of this confusion. This was cheating. It's very easy to cheat. Because, indeed, this type of terrain is the same at all scales. Now, to be the same at all scales is, at this level, an element of purely folklore. And I'll hasten to go ahead and speak of finance, since I spent many years of my life, both in the 60s and again recently, in studying financial prices. In finance, there is also a piece of folklore which says that if you put a price graph somewhere, be careful to put a scale of time, because otherwise one would not know whether these are price changes or prices every minute, every second. Well, that's recent, or every day, every year. It's all the same, goes up and down, zigzags and so on. This is folklore. And I'm not at all ashamed or embarrassed to speak of folklore, because in a field like optics, folklore has been, how to say, taken advantage of long time ago. In the fields which I'm interested in fact, very often, very little was known. Therefore, folklore is very essential, especially if the folklore can be how to say, changed, modified to fit other purposes. Now, what is this folklore about primarily? Now, this edible vegetable indicates its structure. It is cauliflower, obviously. Its most striking feature, as everybody knows, is that one takes a floret as opposed to the whole cauliflower and drops everything else. The floret looks exactly like a small cauliflower. And then can do it again and again several times. Well, it's very interesting that this feature was known to everyone, but I found very little mention of it until my work, perhaps. The cauliflowers are very interesting. They look not from the side, but from the top. And there are all kinds of Fibonacci series, all kinds of structures in them. These attracted very much attention. But I'm not interested here in how to say, precise description of the arrangement of florets on something much more important, which is roughness. Certainly, the surface of this vegetable is very rough. It's very rough in a very excessive fashion, that is hierarchical, the hierarchy. A big thing is made of parts, identical to the big thing, and so on and so on. The parts are well defined. Now, the world in general is not that simple. And in general, this idea of large and small scale parts is, of course, all mixed up and confused. Now, this marvelous graphic is due to my friend Richard Voss to implement a model of mountains that I put forward way back in the early 70s, before computer was able to do anything of this sort. Now, it is not a picture, photograph. It is not a painting. It is the implementation of a mathematical idea. And the mathematical idea is so abstract and so, how to say, devoid of substance that was very much attacked on this account. The idea is simply that there is an invariance between the roughness of mountains in big, small, and very small scales. Now, again, it was not something which I, how to say, quote unquote, invented. Explorers of the mountains, Whymper, who climbed the one Matterhorn, at least was the first man recorded as climbing Matterhorn, wrote about his rambles in the Alps, that a small part of the landscape is the same as a big part, and he had all kinds of philosophical consequences from it. But it was certainly not taken seriously. So what I did here, it was just to embody this idea of wisdom, this wisdom of folklore, and replace it by invariance. Now, one knows the invariances which occur in relativity theory, quantum mechanics, and so on. Here, the invariances are those of dilation and reduction. If you dilate it and reduce it appropriately, it doesn't change. Well, we can go on forever, but I would like, first of all, to give an idea of the nature of the problem and just how it's passed. The idea of fractality, fractal is a word I coined in 1975. The idea of fractality did not exist before, but an intuition of fractality and, in fact, examples of use of fractality go back absolutely to time immemorial. This picture here is at a village in Tanzania of a nation which I don't think lives there. It's a ruin. But if one looks at this village carefully, if one looks mostly from the top, which is less nice photograph, but more telling, one realizes that's made entirely in a hierarchical fashion. There's a whole village here, this thing you see here, which is the harem of the king, then the king's house and so on. Everything is on the same pattern, but more or less big. Humanity has always known of that, but this was decorative device. And the decorative device was known, again, to every country. I chose Africa. I might have chosen just as well temples in many parts of the world. Now we get to a point, or 2 points rather. To the right of this picture, you see the celebrated face of war of Dali. I don't think Dali knew about fractals. To the left, you see this abstraction, which has a long history. It is actually, I saw it, I first discovered myself, quote unquote, invented, quote unquote. And then I realized that a man named Sierpiński had written a paper about it. And I needed a name I called Sierpiński gasket to make it sort of nice. And it has become a very important shape in physics. You see exactly how it's built. I don't know how to tell you. Take a triangle, you take away small triangles. Now, the most astounding fact is that you go to Sistine Chapel, you find approximations of it on the pavement. If you go to churches, you find these kind of structures all the time. It has been all along a very long decorative design. So to summarize, fractals have, on the one hand, a very, very old history, and then this shape, the triangle, was drawn first around 1900. Then there was a period in which mathematicians started distilling them. Did they know about the uses of fractals in decoration? I don't know. There is no record of the telling. However, Cantor, who was one of the greatest among them, did write a record in writing of his thinking, and he certainly wrote to his friend Dedekind repeatedly that we mathematicians are of a divine race, and we can devise shapes that nature does not know. So at least some of them thought they were inventing something. In fact, they were not. They were putting in a very, very precise form some structures which humanity had been always familiar with. And so then the question arises, if you want to begin a science, you certainly must need numbers for it. And the astounding finding was the case at least 15 years ago, that whereas, of course, loudness had been measured very well, pitch had been measured very well by frequency, and the same thing for visual impressions. Weight has been measured, temperature has been measured. That was actually an invention in history by Galileo. There was no measurement of roughness. And I wrote in mid-80s an article with some metallurgist friend about roughness, and he showed me after many examples that in the literature of broken metals, of fractures of metals, there are all kinds of measurements of roughness which are very, very imperfect and very, very unsatisfactory. Well, so I introduced in science a notion which I call fractal dimension, which takes many shapes. I'm going to go very quickly through it. It is a simplification of something which had been used before, used only in mathematical esoterica by Hausdorff. And that simplification, that Hausdorff dimension is impossible to use in science. There's no way to measure it because operations it embodies. The other dimensions are indeed measurable. And in fact, something very interesting happened. You will see that these dimensions can be fractions. And after several years of working with them, in fact, doing nothing else except using them in one context or another, I didn't say I taught myself about roughness, because everybody, I think, knows about that. I taught myself a correspondence between roughness and this number. An anecdote, at one time a friend came to visit me, I had then 2 programmers, to show us a beautiful new construction, and he asked me to guess dimension. My 2 programmers who had no experience of it, one said 1.2 and the other said 1.8, just out of their hats. And I said it's a little bit short of 1.5. It was 1.48. And then I'll come back to an example of where I guessed dimensions 4/3 because of being attuned to it. Again, I don't think that I have a skill which is unique. I established myself a correspondence between this number. Now, how does this number come? It starts with a very, very trivial property of dimension in ordinary cases. You divide a string into n parts or a square handkerchief in n parts. In each case, dimension is the ratio of log of n divided by log 1 over r. Whenever I publish that in a scientific journal, an idiot editor tells me which base. Of course, it doesn't matter because the ratio. Now, you also putting the usual shapes, you take an interval, you replace it by the Zig Zag, made 4 parts, and you repeat again and again. Well, here, if you take log n over log 1 over r, you get 1.26, etc. In the middle part, you get 1.5, exactly. In the right part, you get 2.0. I'm not going to go into details of it. It would take forever. However, this and related quantities have been totally tamed to be measured. They can be measured sometimes with exquisite precision. In one object to which my current latest paper is devoted, the dimension is 1.71 with some uncertainty about the next decimal. It's, well, a little uncertain, not much. But it's astounding that the notion, which is so abstract when properly generalized and so on, becomes so completely measurable. And so let me now bring this matter of 4/3. Now, this picture is my book. I forgot which page. I was very much interested in Brown motion. Brown motion is one of the center of probability theory. Of course, it's a process which was defined by Norbert Wiener in the 20s and was his greatest claim to fame for a long time. It's a drunkard's walk, and you see this black line goes around. And so I was drawing these things all the time, and in a certain sense, I was fishing. What do I mean by fishing? Well, I have the very strong impression that my colleagues and friends just underestimate the power of their eye. Well, there's something else to it. People are more or less good at with the eye. I mean, it's very clear. Scientists are recruited mostly on exams which measure ability to do algebra fast and correctly. So it's not necessarily the case that scientists have very good eye, at least not in mathematics and physics. Certainly in other fields, the answer is yes. But I do have a great dependence on my eye. And I was playing and playing and playing, and then decided that this thing was a bit too diffuse, and the Brown motion was starting here and going around, ending here. So everything I was looking for was invisible. Everything I was looking at had been known before. So I decided, first of all, to have the snake bite its tail by having Brown motion come back to where it started. And that's, again, an idea of Norbert Wiener. It's called the Brown Bridge. And then I decided to color it. Color doesn't mean that I put fancy, colorful things like on these mountains on the Mandelbrot set. It's just very simply to make a difference between inside and outside. So all the points which could be gotten from outside are now white. All the points which are not accessible are put in gray. When I saw this picture first on the screen, I tell you, I became speechless. The picture screamed at me, I am an island. A very complicated island. Now, as Ed has said, how long it costs of Britain, and you can replace any island as you wish in it, is a very basic issue. And the length is quite irrelevant because it depends upon how you measure it. The roughness is measured by dimension. And so I've seen many islands, real ones and fake ones. And this one was very, very irregular. So my first reaction was, about the most difficult islands I've seen were 4/3. 1.5 goes beyond. 4/3 was a kind of magic number. 4/3 was the islands I was very much pleased with as being sort of irregular. Then you measured it, because man can measure it, and the answer was that the dimension was 1.33336. Well, this is a humongous simulation, so you can get these things very accurately. It was 4/3. Now, the most extraordinary thing about that is that if you begin to be attuned to it, you look in these kind of contours for all kinds of shapes. And some people claim that the left part of it is Spain, which had been sort of made bigger, that England, of course, had been vanished because different island. Scandinavia was there a bit out of whack. Anyhow, people begin to see actual geographical features very easily. And that's sort of almost automatic. You do curves of this dimension and you find it. Well, 4/3 was for a long time a conjecture for 18 years. Then a friend of mine, Bertrand Duplantier, gave a demonstration of the 4/3, which was very beautiful but not rigorous. He calls that exact but not rigorous. It uses all kinds of techniques of physics which are probably correct, but are not certified as such. And then shortly afterwards, Schramm, Lawler, and Werner proved it. Now, what is interesting here is not that the theorem was proven. Actually, the proof takes several hundred pages. It's extremely difficult. The techniques of every kind is something overwhelming thing. The interesting thing was the extraordinarily short path between a childishly simple thing, namely a drunkard going around, and then a question which is very difficult, which for 20 years baffled the most brilliant among my friends and was a topic of great despair. First of all, they said, I'm going to do it overnight, then next week, next month, next year. Finally, it took a millennium. Well, it didn't take a millennium, but it had to wait until next millennium. It's very often the case. And I think that actually it is representative of a feature of what I said about roughness, that roughness have not been explored systematically for itself. I mean, I made a lifetime devotion to it, but it was not. Therefore, it is not a case in which simple problems have been solved long ago and only difficult ones remain. Simple to state, I mean. It's also a field which is not very old. So there are very few cases in which a problem arose out of previous problem. Mathematical questions arise out of things which are very, very common. And I will tell you at the end more about my very great commitment now to education. And one of the aspects of education is to realize that even adolescents, sometimes even smaller children, junior high and so on, are very comfortable with the concepts that describe roughness, the concept of self-similarity, the concept of algorithm. I mean, if no obfuscation is added, they understand very well. And then when they see that by a little manipulation, from these very, very simple things, one gets these very complicated matters, I think that we make them understand, to at least some extent, this notion of extraordinary fruitfulness of science in creating problems as it develops. And, well, it's a course at Yale which I expressed very behind with Michael Frame. I will tell you more about that. It's the last line, token of the value of the eyes recent return to pure mathematics. Expression of that is that there's an article about that in a French edition of Scientific American, and the illustrator felt obliged to mark the boundary of this object. The whole point that the boundary didn't have to be marked. The boundary was visible without being marked. You didn't have to mark it. Well, all that cries out for simpler proofs, and I'm going to go further. The critical percolation clusters, I will not go into details of what it is, but the general idea is very close to what the structure of a magnet is. A magnet is made of little magnets going up or down, and there are critical percolation clusters, complicate shapes, and they too have boundaries of dimensions 4/3 and also 7/4, because depending what you look at, you get either 4/3 or 7/4. It was the object of great fascination. These measured after I brought out 4/3, and again, Duplantier did something about it, and Stas Smirnov proved it earlier this year. It's a whole field which has arisen, which now is completely independent of the eye, of course, but which would not have arisen without the eye. And I really think that's very important from a viewpoint of understanding of science to realize that what has happened. The reason why the eye went out of the hard sciences was not, how to say, decision by some committee to neglect it. It was observation that as time went on, new questions did not come from the eye. New questions came from old questions. Also, the fact that once those sciences were established, again, the simplest things were very rapidly done, and then the more complicated things came from simpler things in the field itself. But in the case of the prices of roughness and of the topics I've discussed all my life, the situation is very different. We're still very, very close to the initial basic issues, and therefore the eye has been absolutely indispensable. The eye, and sometimes even hearing. In many cases, I have transformed some signals into noises which are audible, and discovered in so doing that phenomena which previous analysis had declared to be identical were in fact very, very different. They sound very different. Now, I would like to just make one rapid step back to the Mandelbrot set, which I didn't want to spend all my time on, in fact, almost no time. When I became fascinated by the subject, I discovered it and described it in around 79, 80, I started with a definition which is different from the one which everybody now uses. And it turned out that it was very difficult to do numerically on the computer at that time. Very, very clumsy. And so I changed definition, which is a process mathematicians like. But in this case, I changed definition, thinking the two definitions are identical. And the second definition is the one everybody knows. It's very easy to program. And all these incredible riches came out pouring. But, and observations made on the pictures became mathematical conjectures, and they were modified, proven with great success. But the initial idea that the two definitions are identical, well, one set is a closure of the other, that assumption, conjecture, whatever, is still not proven. We use that and Brownian cluster in this course at Yale on fractals for non-mathematicians, and also in workshops for high school teachers, because there's nothing there which has to be left unexplained. Everything is very well explained in great detail, and they understand very well the nature of some problems which otherwise would not be understood. Now, let me change topic substantially, but not so brutally, because what I'm going to say applies not only to prices, but also to many noises, many phenomena in nature, in many fields. But this corresponds to one of my earliest fascinations with financial prices in the early 60s, and then a topic which I very much devote a very big part of my life to at present. Now, prices, of course, go up and down. That was known to everybody, and there are all kinds of nice maxims about it. In 1900, an incredible genius looked at the problem. His name was Louis Bachelier. Nobody noticed him. He had a very miserable life. But he wrote in 1900 a thesis, PhD thesis in mathematics, believe it or not, called The Theory of Speculation. Speculation meant speculation on the stock market or bond market. And he introduced for the first time in loose and incomplete fashion the Brownian motion, which Wiener later made into a central mathematical topic, and which in between Einstein and others made into a central physical topic. Now, the idea of Bachelier was more or less that prices vary at random. You can't predict them. You toss a coin. If it's heads, your price goes up. If it's tails, price goes down. And you go on and on and on. Well, you can approximate that by a sequence of independent Gaussian variables, and you see it on top very clearly. The sequence of independent Gaussian variables, which are the increments of Brownian motion. It's called also white noise. Carelessly called white noise, which we call Gaussian white noise. It makes a very big difference. I'm going to argue in a second. Now, much later, a whole theory of stock market occurred on the basis that this model Bachelier is indeed a representation of reality. And the size of these increments of price, this size is what's called volatility. The model assumes constant volatility. And indeed, if once you have seen a little piece of this line on top, you have seen them all. They're all very much alike. And if you average it, if you take averages, moving averages, this whole thing goes to zero very, very quickly. Now, look immediately at the bottom 5 lines. Skip 2, I'll come back to them later. At least one of them is a real price series, price changes. Or at least one of them is an illustration of my current forgery, which is called the multifractal model of price variation. Now, I'm sure that many people here are such great geniuses that you are going to guess immediately which is which. But you are exceptional. Most people can't do it. Because all these phenomena have a very strange characteristic that have very big peaks all the time. And the peaks don't arise by themselves. They arise in the middle of periods of great volatility. Then there are periods of very, very low volatility. There are periods of volatility, so it changes. Volatility, as you try to grab it in these sequences, either the fake or the real ones, is something very, very, very elusive. In fact, it's impossible to grasp. And so how are we going to represent those phenomena? And I put this example in particular because it puts in contrast very, very sharply the approach to roughness, which has been used by, I think, most authors before Fractals, and the approach to roughness, which I've been advocating. And I would like to emphasize differences without going into long calculations. The approach which most people have been advocating is if a constant volatility phenomenon doesn't work, then replace it by something which is a variable volatility. And if that doesn't work, then replace it by something at discontinuities or jumps. Well, this is very much the spirit of the celebrated model of the motion of planets due to Ptolemaios. In the Ptolemaic model, the planets go around circles, and then there are epicycle cycles, which are, and then the epicycles, planets go on circles, which center of which goes another circle. And then, in addition, one must assume that the center of the basic circle is not identical to the center of the universe. In fact, there are three factors. Everybody knows that how Kepler replaced that by a different formula, which later Newton transformed by explaining it through gravitation. But the main fact is that there are two approaches to this phenomenon. Either that the prices which are in the lower part are just other examples of something complicated and pleasant, which are just combinations of the simple, or that there is something radically new which is involved. Now, I'll tell you about how radically new the thing has to be. Many of these very big peaks you see on the 5 lower lines exceed, well, something which is defined as standard deviation. Actually, I don't know how it's exactly measured, but sort of 10 times bigger than the standard deviation of the most examples. They're called 10 sigma events. Now, 10 sigma events in a Gaussian process, Gaussian independent process on top, the probability would be 1 millionth, a millionth, a millionth, a millionth. The inverse of Avogadro's number. It's a very small number. If that were the case, these things would never happen. But as you see here, they happen all the time. So it's not a matter of adding a little bit of large values, because one gets a situation in which the large values dominate everything very strongly. As a matter of fact, I'm going to go a bit illogically to make a point early on. The central aspect of statistical physics, statistical thermodynamics, is that a big system evolves in a certain way, namely entropy increases with probability 1. With probability 0, entropy is going to decrease. But the events of probability 0 are totally negligible. The events which count are those of probability 1. Averages, of course, converge. The past and the future are independent. All kinds of beautiful theorems apply. But if you go to financial prices, it's again part of folklore. If you look at last 10 years and the wonder, assuming that somebody with miraculous powers of seeing in the dark, some devil, would pick the days that matter, you'll realize that the days that matter were just 10 days out of the last 10 years. Very few days mattered, and the great fortunes were made in very few days. Great ruins happened in very few days. So one gets ultimately into a situation which is very, very unsettling. That is, in this context, only the very few rare events count overwhelmingly, and the rest doesn't count, counts hardly at all. It's a way in which, context in which one must review one's intuition very strongly. But reviewing or not reviewing, it's best not to abandon solid ground and abandon the principle of modeling, the primary principle of modeling, which is that of invariance. It becomes almost a joke, I said before, to others. To what extent some scientists, I'm one of them, emphasizes that the basic trick of science is invariance. You find the right invariance. And in fundamental physics, you look for all kinds of new invariances. And the lucky ones or the perspicuous ones are the ones who find better theories. In this case, the matter was to find the right invariance. And so I'm giving you the key. The forgeries which I introduced among these lines were not chosen by taking the line on top and adding this, adding that, adding this, adding that, until the thing looked more or less reasonable. It can be done, but I don't do it this way. The key is to find the right invariance. And lo and behold, the right invariance gives this result. Now, let me again take a step back, because it's a lesson which not only applies to this financial crisis, but to many other phenomena. Believe it or not, but the 5 bottom lines are all white noises. I repeat, they have a spectrum which is constant. There's no correlation. But everybody says, but it's full of very interesting structures. How can a white noise be so interesting? I'm used to white noise like on top, which is boring, which is like you've seen one redwood, I've seen them all, like former President Reagan said. The bottom, everything is different. Well, the fact is that the bottom 5 lines are not Gaussian. Therefore, if not Gaussian, whiteness does not imply boredom. Whiteness implies very often a very rough ride. Now, the second idea, so the tool of science, namely the spectrum, which had been marvelous, is not applicable in this context. It doesn't work. I mean, again, Wiener was very clear when he described spectral analysis early on. As you realize, Wiener was one of my intellectual heroes. When he described it, the conditions under which spectra are good, but these conditions are not satisfied for these data. Now, is that a new finding by Benoit Mandelbrot that these are white? By no means. I remember when spectrum became usable after the fast Fourier transform was rediscovered. It was rediscovered, actually. Everybody went on to spectral analyze everything in sight, and prices were spectral analyzed. They turn out to be white, price changes. And the result was absolute horror. How can it be? If it's white, it should be like the line on top. Now, every book of mathematics says that independence and orthogonality are the same for Gaussian processes. Orthogonality means a white spectrum in this case. But nobody pays attention to it because the examples given when they are different are very made-up examples. These are not made-up examples. These are examples made by culture, insofar as the stock market is not part of nature. Therefore, it's part of culture. Or made by me, which is also culture. But so you can have structures in this fashion. Now, the other thing is the habit came from thermodynamics that if you take a big enough system, then fluctuation don't matter. In fact, the whole thing was proving bigger and bigger system, ultimately fluctuations do not matter. And they average out. But look at the thing on the left. It is not quite the same thing on the right, it's the squares of it. And there's some hanky-panky to it, but it's about, roughly speaking, variation of prices over a century. If these little things on the right were just fleeting defects which average out, then over a century it had been very, very smooth indeed, and certainly not smooth at all. So we deal with phenomena in which averaging does not really make any simpler. And that's, again, the signature of invariant processes. The same as small scale and big scale. Self-similarity or variance thereof enter into this game. And so let me know, so the models, I'm going to say a few more words about that, multifractal models, but the second line on top was my first model of prices. I call it mesofractal. Now it's a new term because I need these terms for various reasons. At that time, I was so focused on large values that I neglected the dependence between prices. The bottom lines show you that prices have enormous dependence. I mean, that's why people can, there's a great deal of prediction actually possible, and well, in one form or another, but that's a different issue of here. But the second line was independence, have these very long peaks, and that took care of one of the problems, which is the long-term dependence, the long tails, the large values. Then I had another way, the second line to take care of long-term dependence, but only multifractals took care of both. And it's interesting that multifractality is a notion which I introduced in about the time I met Ed Lorenz, a matter of fact, a little bit later, to explain the nature of dissipation of turbulence. Not explain, I'm sorry, I take it back, of describe it. Explain is a big word. Describe because it's a topic in which truly the natural tools borrowed from other successful sciences have been quite unsuccessful. Now, let me explain to you how here this matter of self-sameness, which is no longer self-similarity but self-affinity, enters around. So this is not a model of price change, it's a cartoon. What's a cartoon? A cartoon is something which has recognizably the same features, but which is simpler to draw and to behold. So on top you have a straight line, a trend, which the price change from beginning to end. I was told by all means it must be going up. So it's going up. And then there is this variation of this price, which is the second line, which I call generator. It goes up, up, down, up. And to simplify it, I make it symmetric. Then for each of the next stages, what I do is to take this generator and squeeze it. But you see, you must squeeze it in different ratios, this way and that way. If the ratio of squeezing were the same both directions, you would deal with a similarity, and the thing would be self-similar. If you squeeze at different rates this way and this way, it is an affinity mathematically. Therefore, these things are self-affine. And if it goes down, you turn the thing back. You do it again and again. Now, after a while, you get this jagged curve, which has a certain amount of boring regularity. So you inject the minimum amount of randomness. And to do so, you simply, before you introduce the generator, you choose at random between three possibilities: down, up, 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 down, up, or up, up, down. Very easy to simulate. And then here is what you get with different on top, with the values you saw in the previous picture, you get the sequence, which is more or less what Bachelier was saying, more or less what the conventional so-called theory of the market supposes, coin tossing or a variant thereof. Then what you do is, to come back to the previous thing, you move this top point a little bit to the left. So you just, you have one parameter here. You see one point parameter. The point parameter is the first break, it determines the generator. And so as you do it, you realize that suddenly this thing becomes more and more irregular. Now, this is all there is to it. It is not an incredible accumulation of cycles, epicycles, not center circles, etc., etc. It's simply self-affinity. These curves are increments of a self-affine process, which is self-affine by construction, because you do it by this recursive process, which has the minimum amount of randomness, namely shuffling. And at the end, you get something which is no longer realistic for a stock market, because it seldom happens that you have these periods where almost nothing happens. If you went further, you go even further. So you can go beyond what you observe in the stock market. Now, I don't say it's a model. I just say that it's a case in which the first investment gives a high yield. And I have been in many sciences, and I'm also a history nut, so I read records of many early days of many successful theories in science. And there is one theme which runs through them, which is that the first stage was awfully simple. And it gave interesting results. Then, well, bells and whistles were added, but only gradually. And that those theories, which began by design, which was full of bells and whistles to make it look right, never take off. They're just too overburdened to begin with. Now, I don't say this one is going to take off. It's very widely respected. It's very widely criticized. It's very widely hated. It's very widely, et cetera, et cetera. But the point is that it provides what I think was necessary in this context, to have an extremely short, no bells, no whistles path between folklore and a quantitative, measurable, realistic, and also realistic representation of data. But now, here is something which is very disquieting. So you see on top of these things, this little zigzag, it's not the same zigzag before, but again, you just take zigzag and you do it recursively by changing the sequence each time. And so these 8 sequences of increments are identical from viewpoint of the process that generates them. And here we get into one of the most constant and the most, in fact, perturbing features of fractal phenomena. And perhaps I would first oh no, let me just comment on that. If you apply to these 8 processes the usual techniques which are applied to randomly varying phenomena, you find that they're all different. The variance is different, the correlation is different. Well, in this case, not even white, because I didn't make sure they're white. It's very complicated. If you apply the right techniques, which are techniques of multifractal analysis, which are developed for the purpose of measuring roughness, then all these 8 are the same. Let me come back now to this matter of metals I mentioned earlier. So Dan Passoja, who was a metallurgist, was getting from whoever, National Bureau of Standards, or maybe it was already different names, sort of finger-shaped piece of metal. In fact, they came in large numbers. So the National Bureau took a piece of metal and had an extraordinarily careful treatment to a very expensive piece of metal. They were very carefully treated at constant temperature or for a long time, so to be homogeneous. Then they were cut into 5 pieces and sent to different laboratories who ordered them. We cut them bang, 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 bang. We measured the roughness as the book of metallurgy said it should be done. And that measurement was, lo and behold, exactly the same as the measurement advocated in the books of finance. That is, you approximate this mess by a straight line or by a plane or whatever, and took at the root mean square deviation from that level. And you assume the root mean square deviation is a measure of non-flatness. Well, it is a measure of non-flatness. But the horrible fact was that we had 5 samples which the National Bureau of Standards guaranteed to be identical, and the measures of roughness were all over the landscape. So they didn't measure anything. If you measure the root mean square on these things, you get results that are completely all over the landscape. These things are totally different. They suggest an extraordinary level of variability. However, if then we measured these fractures, when you measured the fractal dimension, not quite as simple as what I wrote to you, but the next simplest algorithm which makes it measurable, we found in all cases, lo and behold, hold your breath, 4/3. Well, not quite 4/3. 4/3 for lines, and it's a normal dimensional line is 1, a curve. So it's plus 1/3. And for surfaces, 2 plus 1/3. So then people redid the experiment on very much longer samples, and they found that indeed the 4/3 holds over 5 orders of magnitude. That is, here is a case of roughness in the most, if you forgive me, the roughest form, the roughness of a broken piece of metal. By looking at the wrong measurements, you get values all over landscape. By looking at the right measurement, you find that a certain value can be measured over 5 or more orders of magnitude. The heat treatment only changes the crossovers at the end and makes the range bigger or smaller. But the precision of that is absolutely incredible. It's also true for glasses. It's true for a variety of extraordinarily different surfaces. Rough surfaces have this property of plus 1/3. Now, I view that as being first of all, an example of a mystery of nature reduced to a manageable, concise, and clean conjecture. It is not a complicated statement about structure of metals. It's a simple statement. That thing is 4/3. And it is, of course, the greatest clear success, greatest token of success for a model which say that this is the way they're measuring it. Now, after having given you this example of construction, I want to describe these diagrams. In physics, it's very important once you have a certain model to change some characteristics, temperature, and something else, and to have a phase diagram in which one sees how the properties of a system vary. And so these are three ways of showing it for the symmetric, again, going back to prices for symmetric generators. Well, let me show this and I come back to the previous thing. This is, on the left and the right, a test which tests whether price changes are indeed, do indeed follow the multifractal model. Here, the price in question is the exchange rate between the dollar and Deutschmark, which had the advantage of being a rather clean, finite sample, since on January 1st, it will stop, since the Deutschmark will vanish. It is known for many periods with excruciating precision every 20 seconds. You can have data in this context, which are data like one never thought one could find in the context of economics or finance. They are data like in physics in the best cases. So one does this diagram, and the tau of Q is the conventional name now for the slopes of that thing. I don't want take time for that. On the right, there is this envelope of these lines, and this envelope is called f of alpha. And these things are the fundamental characteristics of the processes. So to come back to these, if one did the same analysis of these on these 8, you find the same results. Again, every analysis is not appropriate to find very different results. So here is this matter of a Manichaean view of the world. When I described to you in the beginning that the rough versus the smooth, of course I have in mind the fact that even though smoothness is so rare in our experience, it was transformed into geometry in a marvelous fashion. And I was myself, as a young man, totally immersed in classical geometry, the most wonderful thing one could imagine. By this kind of extraordinary miracle, it gave rise to a description of nature, beginning by ellipses being good for Kepler for describing planets' motion, etc., etc. The whole of science is dominated by mathematics, which is that of smooth. And that mathematics arose early on. Derivatives, of course, are part of it very strongly. And most differentiable manifolds and so on, you find these words differentiable all the time. These are the primary objects of mathematics, and in particular of science in gravitation and light. But now we have that the situation that in some parts of nature, things don't fit in this mold at all. So by this belated process, which started with very abstract mathematics, we're trying to get separate from physics. Again, remember these words of Cantor, which I find totally extraordinary, that mathematicians can feed themselves from nature. By trying to feed themselves from nature, they introduced these concepts and related ideas, which were called mathematical monsters and the like. Poincaré was making fun of Cantor and Peano by saying that in the past, mathematicians were inventing new shapes to help us understand nature, but today they invent new shapes just to annoy me. Well, it was the case. And so the central point of fractal geometry is that actually Cantor was just plain dead wrong. That these shapes were not, the way they were invented is irrelevant. Whether he knew of decorative schemes or not is irrelevant. This mathematics was actually necessary to take a first step for study of roughness. And so that brings again in very strong relief this question of averaging, which destroys randomness. The classical pattern was that of thermodynamics. I don't know whether anybody teaches that any longer, or classical thermodynamics in which randomness didn't exist. And then there was statistical thermodynamics in which energy was not a constant, but was fluctuating a little bit. But so little. Only fine electronic measurements could pick the thermal noise, and that was discovered only rather recently, namely about the time I was born. For everybody, that is the definition of recently. But the phenomena we deal here are not like that. Things don't average out. And so what I have developed increasingly over the years, gradually, but focused now very strongly, is again a view which I would like to give you more or less to finish this talk, of states of randomness. Now, in mechanics, we all agree that the laws of mechanics are unique. Well, forget about details for the phenomena we're looking at. It's all classical mechanics, Newton and so on. Laws are unique. However, if you look at the assembly of molecules, it matters very much whether the temperature and pressure are such that the whole thing is a liquid, a gas, or a crystal, or a solid, as I used to say. It matters very greatly. So one does not begin by starting everything ad initio. One first looks, it's a gas, I know which tools to use. It's a liquid, I know which tools to use, even though liquids are pretty horrible stuff. And solid, I know which tools to use. Now, in randomness, this was not at all emphasized. It's emphasized that there is a beautiful axiomatic, good for everybody. But then once you go to practice, especially practice in physics and engineering and finance, one always looked to phenomena in which averages, everything sort of averaged out to limits very quickly. There was no randomness after a certain time. But the phenomena which I study, whether it is in nature, and that means turbulence or whatever, or in culture, that is stock market, or everywhere, these phenomena do not give any evidence of being averaging. I call them wildly random. The very simple formulas in that context give very complicated structures. I would like to end up by one thing. I say I was ending, but let me just add another point. At one point, I was very much attacked by my friends, mostly my friends. My enemies did not even bother, because I was describing an alternative view of nature, which was so different from the view based on smoothness. Smoothness includes, of course, everything which is ruled by partial differential equations, Laplace, Fourier, Poisson, Navier-Stokes. And this thing had no differential, no derivatives, had strange behavior, and so on. So do these things belong to different universes? Well, I don't think they do. I think it's just very unified. I think that partial differential equations, if pushed beyond the conditions under which, rather stringent conditions under which solutions are unique and smooth and differentiable and everything, they give rise to very complicated behaviors. And one example of it is that if you take a large assembly of particles interacting by inverse square root attraction a la Newton, if you start with Poisson distribution or just a lattice and put some pinch of energy to start it, after a very short time, you see that these particles become extraordinarily complicated and reassemble themselves into a fractal universe. I didn't mention fractal universe until now, but I would like to say 2 words about it. The distribution of galaxies in this universe is fractal. There is no density. All kinds of things occur which are quite new. Well, that would suggest that, the clustering of galaxies could very well not be due to specific complicated forces which we don't know, but the simple behavior of particles under 1 over r square attraction. And so that raises the question, is clustering up there in the sky or is it up there in our head? Well, it may well be in our head. I don't know, but it's a question which has to be discussed. In fact, one finds that many of these questions become very, very much revised. Now, if one begins to include the fractal of the universe, oh yes, it's a fact. Early on, which is sort of 20 years ago, when I wrote my book, the universe was expected to be fractal up to 5 megaparsecs, 15 million light years depth. It's nothing by universal standards. But then it crept to 20, to 50, to 100. I don't know. It's between 200 and 300 for most people now, and many people believe it's 1,000, which is pretty far. So if it is true that the universe is fractal up to that level, then fractality will insert itself into cosmology in a very strong fashion. Therefore, not only fractality will be a result of very simple laws of physics, like 1 over r squared, possibly, but to affect our understanding about the order matters. Well, I must stop here because things become more complicated, become very complicated, and this is not for this lecture. I've been writing on this topic for a very long time, as you see, and also for those who are interested in finance, the journal Quantitative Finance has several papers in the current year on that. I publish right and left. That's my book on finance, my book on noise. I would like to end by this one, which is coming out in a few weeks, or a few days perhaps, by Frame myself on mathematics education. We find, to our utter amazement, that humans like fractals. So, and I won't mention anything about art, but this was a result of a very, very, very poor programmer's work. He had some bug, a semicolon or something dreadful. He gives his result. He started apologizing, fearing to be fired. I started thinking from the bottom of my heart, and before correcting the bug, we had this picture taken. It's something around the Mandelbrot set. Mistake was made, but it's a whole topic unto itself that humans seem to be happy with roughness. You must have the same experience as I do, because you say a mathematician, oh, people say, I find mathematics utterly dry and dull. Well, I don't, but they do. This is one part of mathematics, and that's mathematics of the flat and the smooth. The mathematics of the rough, as developed by many people 100 years ago, and now it's galloping development on all sides, never gets these reactions. In fact, they say, if I had only had that in high school, I would have loved mathematics. Well, you don't need to be told that mathematics is lovable. But it's only at my old age that I dare present my life and the story of science as being a conflict between two forces. One, the force of good and bad, the evil. You choose which one is which, smooth and rough. But I think it has illuminated my view of how things occurred. And the reason why roughness came so late, why it's so difficult, is because it simply is more difficult. It requires different mathematics, which was developed only very recently, which is developed now for the purpose of this investigation. It requires just a different viewpoint. But it is, I think, definitely a frontier of scientific investigation. Thank you.
Thank you, Professor Mandelbrot. We have time for a few questions. We have two microphones up here, but you've managed to fill in the density of the auditorium sufficiently high that we may have some trouble getting to them. So if you want to ask without the benefit of amplification, please speak out as well as you can. Do we have any questions? One over here.
As a high school teacher who is trying to get all students to be good mathematicians, to apply themselves and so on, how much of fractal geometry can I use?
I think much more than you think, and much more than I thought not so long ago. We have now for several years at Yale workshops during the summer for high school teachers. So we get the cream of Connecticut, so they are the best. But they tell us stories which are quite incredible. They ask us about how early can I bring it? Is junior high right time? Some people say elementary school. One of our friends, we have a kind of network of friends all around who have been using these techniques. Some of our friends have tried with the kindergarten children. They put them blocks. The blocks had O or I or X. And children play with that. Then you put other fractal things, and the challenge is to rebuild the fractal by putting these things in a certain order. The kids become so absorbed, apparently, that they are lost in, because that's a real task. It is not a task which you, the teacher, has imposed. It's a task that nature has imposed on humanity for forever and forever. And so in junior high, it's very easy. Everybody who is anybody learns how to program at 11, which puts me to shame because I never did learn to program. So it should be early. And in a certain sense, the question of whether this is the right mathematics to begin with is the wrong question, because the mathematics of the smooth has been so elaborated, has become very, very far from my experience. And the questions it asks are so refined that it is not questions which come naturally. They're not questions about anything Unbeam has thought. The Pascal's theorem about the circles, I was a geometry nut. I loved that, but I was the only one who loved it. For all the others, it was an artificial thing that somebody in Pascal just made to bother them. But question about mastering roughness, which after, again, the rule and not the exception, smoothness is engineering. This table is smooth, well, not quite so smooth because it's already several years there, so it has some roughness. I'm sure fractal, but on a good approximation, it's smooth. It's engineering, which is cold, which is dry, etc., etc. So if mathematics can go back to its origins, and it is not even something which is artificial. For example, I mean, give you an example why. I'm discussing that with a friend the other day. I introduced a notion which was taken as being the end of madness, that of negative dimension. Now, you measure things, so you measure roughness, and now you can also measure vacuity, emptiness. So listen to that. If you take two lines in three-dimensional space, their intersection, well, they don't intersect, of course, but intersection of lines is less empty than intersection of a line and a point, or of 2 points. That looks like science fiction. Actually, it's a question which arose when friends of mine were looking at intermittency of turbulence in the laboratory, because I could explain why. It's a long story. But then, to explain it, we must understand that lines are not lines. Lines are little tubes. And lines being little tubes is not only an invention of me, it's an invention of Minkowski, who was a very great man in 1900, and who pointed out that one gets away from all kinds of horrible paradoxes in mathematics by never thinking of lines are lines, or surface as surface, but thinking of lines as being tubes, surface as being comforters, etc., etc. So when it goes back to these things, not only when one goes back to Mother Earth to get strength again, but one does it in a fashion which is fruitful. Because without this element of going back into epsilon neighborhoods, to call them by a fancy term, one could not make sense out of negative dimension. And negative dimension is something you can measure, and which is a useful thing in the study of turbulence.
Do we have another question?
Are there any human behavior in fractal terms?
Well, certainly stock market is a human behavior. As a matter of fact, I have come to use the word culture in a sense which is perhaps not smooth to some ears. I was speaking fractal geometry of nature, and then giving an example like stock market. But take example of internet. It's human behavior. It's not exactly what you think of human behavior, but a large number of very brilliant people working at cross purposes put these things together. And it works marvelous most of the time, and every so often it's terrible, and your messages don't go through. But so people first try to apply to the internet the techniques which had worked for telephones with Poisson behavior and so on. It was absolutely off the mark. it is multifractal, and it has to be multifractal. Now, after the fact, it's understood. So here is the human behavior, and because design of this very informal and noisy and messy design of this huge system, which for reasons which are after the fact sort of vaguely understood, is multifractal, but you don't have to understand it to live with it, because you have to live with it. And so if you make new equipment, you better test whether its properties will behave well in the face of it. But I was trying to start with human behavior, which is not usually counted as such, but art is certainly human behavior. And so does art have fractal aspects? Certainly. And let me give you an example of that, which I still find mind-boggling. My friend Richard Voss had found experimentally that music is one of ref noise, like the things I was showing you here. He was a physicist, and he's not a loud person, so it was sort of, didn't become very widely known. But then I was approached independently by two composers, one in New York and one in Europe, and you must know their names, Charles Warren and George Ligeti, who told me that looking at my pictures made them understand the nature of their craft. And asked for each, how come? And they say, well, I'm speaking in the voice of either, because they give exactly the same explanation. I have been trained in a very classical conservatory tradition, so I knew very well about all the instruments, their values, about everything, but I was not told one basic thing, which is what distinguishes a piece of music from a collection of noises. And I learned, they said, each of them said, by trial and error. I brought the composition to my teacher. He said, oh, too busy. And I brought another composition. It's not decorative enough. And another composition, it just goes up and down too much. It doesn't go up and down too much. After a while, I finally understood what to do, and I've been doing that very well. And I'm sure that you know Ligeti and Warren, they are very famous people. And then look at the picture, I say, but it's obvious. It's obvious, except nobody told me that. It must be fractal. That is, a sonata, 21 minutes, 3 movements, allegro, lento, presto, different. Each movement, loud, soft, very loud. So the thing must have structure at all scales. Something must be changing at every scale. And that's it. If you get that, you get at least bad music. And bad music is much better than noise. And everybody thinks bad music. And Voss was telling a story about he did some pentatonic music. And the Chinese say it's bad Korean music, Korean bad Japanese music, Japanese bad Thai music, whatever. But it was music of some barbarian race. So that's the essence. It's not at all fundamental. Again, good and bad music are together. No, so I can go on and on. Painting. So in the classical landscape, which is a very artificial form of art, both in Oriental and European tradition. So there was a big tree which framed it, and then this little man and so on. All these rules of composition. If you look at it, one big thing. And most of these books of art did speak of design. And I tell you, when I did this cover, I do my own covers for my books. It's kind of, well, I like to do it. So this book for teaching has every single cliche of composition, because I felt it would be effective. So, but on the other hand, I was looking at the film of Kandinsky painting one of his paintings. It looked exactly like a program to do fractals would look. He would look at this piece of thing, and then, boom, a big line, solid line. You see that in all kinds of compositions. Then he would set small lines. When the film ends, has a small brush, and he's adding little things all over the place. So he puts big, small, and medium and so on elements of scale, which is exactly the kind of basic bottom fractality. I could go on forever and forever. So the fact that this is speaking of current behavior, but if you look at this African village, so this behavior is not in the sense of a physiologist, but in the sense of the artist. Now, physiologist, that's not a matter. Now, many of my friends tell me that they have nervous recordings which look like these things I showed. I'd be very much interested in seeing them. But I know very well that if you describe some surfaces in the body, that is certainly human behavior. Some surfaces are meant to be as small as possible given their volume, and others as big as possible. The skin should be smooth and taut like a young child's skin, and the lung inside must be as confused as possible. So the two criteria of design lead to either smooth shapes or to extremely convoluted shapes, which happen to have fractal features. The human lung, for example, is branching fractal on 23 levels. 23 levels is a very healthy bifurcation. It's a very healthy number. It's 1 million.
I think we're going to need to wrap up right now, but I'll invite all of you who want to stay to come on down and speak with Professor Mandelbrot for a few minutes. And I'd like to conclude by thanking Professor Lorenz for joining us today. And let's give thanks to Professor Mandelbrot.